Hello, we're now going to look at the fitting of a factorial analysis of variance model to data. The data derived from Sokol and Rolfe, who presented information on the amount of lard eaten by male and female rats. They were presented with either fresh lard or, in other cases, rancid lard. And here I've listed out the data in terms of the consumption, the total amount of lard eaten, the sex of the rat that was given the lard, and whether that lard was fresh or rancid. Now, at the start of any analysis, I fully recommend that we visualize the data. And since we are particularly interested in interactions in this case, then an interaction plot is probably the best place to start. So here's the interaction plot where we define the factor sex, the factor tasty, and the response variable consume. And what we can see here when we evaluate this plot is that fresh lard does seem to be consumed at a higher rate than rancid lard. There may be a small effect of the gender in that males seem to eat slightly more than females, but that might be just a small deviation in the sample means. But most importantly, there's nothing subtle going on in that the response of females seems to be pretty much the same as the response of males when presented with fresh and rancid lard. If there was something really complex going on, then maybe you'd even get crossed lines. For example, males might prefer rancid over fresh, and yet females might prefer fresh over rancid. So whether or not fresh or rancid was consumed more depended on the sex, and that would be an interaction. Now let's go ahead and actually fit some models. The first and most obvious model is this model here, where we fit the full factorial design, where we've got consumption is fitted with two predictors, sex and tasty, i.e. the state of the lard, and we have, of course, an interaction as well as the main effects here. Let's plot out the analysis of variance table, and what we can see here, working backwards from the bottom up, is that there is no evidence of a significant interaction. There is, however, evidence that the state of the lard has a significant influence on the amount consumed, and we've seen that already graphically. And yet there's no evidence here to reject the null hypothesis that the gender is completely independent of the consumption, i.e. that there is no difference between males and females in terms of the consumption. Okay, well, let's evaluate the model predictions, and to do so I'm going to plot a pair of graphs side by side. Here's how I get the side-by-side graphs. And here is first of all the plot of the residuals against fitted values to check whether the residuals are all approximately homogeneous. And here is a QQ plot, which would appear a straight line if indeed the residuals were normally distributed. Now typically we'd leave it at that. We would see that there is no evidence of a significant interaction, but the state of lard has a very significant effect on the amount consumed. You might wonder, would we get a different result if we change the order? For example, we had tasty times sex as the predictor combination rather than sex times tasty. Well, in this case, because we have an orthogonal design, i.e. equal amounts of replication for each combination of those predictors, then we wouldn't get a different result, because in this case the predictor variables are not at all collinear, they're not at all associated with one another. How about a type 3 sum of squares? Well, again, our design is completely orthogonal in that we've got equal replication across all treatment combinations. And under these cases, the type 1 is equivalent to the type 3 sum of squares. Well, what about if we didn't have equal replication across our treatment combinations? Well, under these cases, the type 3 sum of squares would potentially give us a very different answer from the type 1 sum of squares because we're partitioning data in a rather different way, and under these cases our predictor variables would be collinear, at least to an extent. Now, the subject of type 3 sum of squares when it comes to analyzing factorial designs which are unbalanced is somewhat controversial because it violates the principle of marginality to test for a main effect while controlling for the effects of an interaction which involves that same factor. However, it's still done regularly because it's actually the default of a number of statistical packages like SPSS and Minitab. So I'd just like to show you how to do it if you ever needed to do so, but bear in mind it is somewhat controversial in an unbalanced design. The way we can do it is that we can call up from a function from the car package, and first of all we'll load the car package. Now the function is the capital A ANOVA, and we simply have to specify type 3 sum of squares. But for these types of design we've got to do something else, and it's a little technical, but when we formulate a model, we would typically have to specify the contrasts in terms of creating the underlying model structure. And when we do a capital A ANOVA with type 3 sum of squares through the car package, then we will run into a little problem unless we change our default contrast. So this is what we're going to do here. Typically they're treatment contrasts, but here we need to make them some contrasts. Well, once we've done that, we can simply specify the fitted model. Again, it's exactly the same, and this time run the capital A ANOVA, specifying here that we wish to fit a type 3 sum of squares. Well, in this case, of course, as we anticipated, we get exactly the same breakdown in terms of the sums of squares and overall significance of our individual predictors, because there is no collinearity whatsoever between them. We again see that we've got a very highly significant effect of the state of the lard in affecting consumption, but no effect of the interaction or the gender main effect. Thank you for listening to this R Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.